must not stop at N and LO. They have to go to the next order and perhaps the next order. That's the current enterprise. However, we have the other problem, which is the one that is alluded to by this guy here. This is the vacuum energy of the standard model. And to the extent that the standard model works up to a scale of the order of a TeV, you expect that to be of order a TeV to the power 4. Now, strictly speaking, a field theorist will correct me, a vacuum energy is not calculable in field theory. You can in principle add counter terms and cancel it at every order. But in order to be in any sense natural, it has to be of order m, otherwise you have to cancel it to, as it says here, 1 power in 10 to the 60 in order to be consistent with cosmology. And it is this which is memorably, Steven Weinberg called it the bone in our throat. This is the biggest problem that there is, with no offense to my condensed matter colleagues. This is the biggest problem that we have in, certainly in fundamental theory. We don't understand vacuum energy and how it couples to gravity. Einstein tells us all forms of energy density must couple to gravity, and yet, if it did so, we would not be here talking about it. As soon as the temperature of the universe dropped to the weak scale, this vacuum energy would have become evident, and the universe should have gone off into exponential expansion forever, or since we can't even calculate the sign, it might be a negative lambda, then in that case it would have collapsed back to the singularity. None of these things happened. We are here 14 billion years later measuring expansion rate of 70 kilometers per megaparsec, very slow. This is a huge puzzle, and the only answer to this that I found very categorically given was by Wolfgang Pauli, who said, it is obvious that the 0-point energy doesn't produce any gravitational field. He didn't say why, he simply asserted it. And indeed, recently people have been asking whether de Sitter space, which is what a space dominated by lambda is, an exponentially expanding space with no future infinity, whether that is actually forbidden by considerations of the most fundamental process in particle physics, scattering of particles. You have plane waves coming in from infinity and going up to infinity, governed by the S matrix, which just expresses unitarity. Is unitarity violated necessarily in de Sitter space? This is a question that occupies many of my colleagues. But I'm simply trying to give you an overview of just how fundamental the cosmological constant problem is. And again, I should say, without any disrespect to astronomers, I don't think they really appreciate this. This is why they glibly talk about lambda having a value of whatever it is they call it, which they derive from a sum rule. If they actually understood how serious this matter is, they might think again about asserting that it fits all the data and therefore you must accept it. Now, experimentalists of course like a challenge. If in fact there is a scale in the universe which is set by lambda, that would be a milli-electron volt, as I told you, in terms of distance, that's about 0.1 of a millimeter. You would expect a change to the law of gravity at a tenth of a millimeter. And that is shown here in terms of searches for a departure from the usual inverse square law by adding some, parameterize it by Yukawa-like term, and you look for the coupling. Alpha should be of order 1 if there is indeed some change. Now, amazing experiments have been done to push that down to something like 1/10 already, a factor of 10 below where you would expect it. This is, of course, very, very difficult experiments, testing Newton's law, 1 by r square law at 0.1 of a millimeter. Van der Waals forces are very, very important there. So this is about the best that has been done to date, but it may not be good enough to rule it out altogether, but it nonetheless, they have not found anything. And similarly, people have come up with all kinds of ideas for gravitational screening and chameleon forces, which I frankly find rather contrived. But again, experimentalists have managed to rule out most of this stuff. So the big question is, in the standard picture, omega lambda is of the same order as omega matter. Actually, that's just not a coincidence, that's how you derived it. But people then start worrying about it, because after all, omega lambda is constant in time, whereas omega matter increases as z cube, as you saw earlier. And therefore, at the time of the last scattering, z was 1,000, matter density was 1 billion times larger than today. Lambda was the same, it was negligible. The universe was very close to Einstein de-Sitter at the time. It has only become lambda CDM within a redshift of 1 very recently, within the last few billion years. So people will try to address this by making lambda dynamical, and this is actually become of interest in the context of what is called the swampland in string theory, because lambda is perhaps forbidden in much of that parameter space, but this is allowed. What this is a field which has a potential with the height of the required value, milli-electron volt, but its web is at the Planck scale. Its curvature is no larger than the Hubble parameter, 10 to the minus 42 GeV. So if I wanted to draw a potential like that, like a Mexican hat, if I put it at the height here at say about 1 meter, then the minimum would be beyond the horizon of the universe. It's such a flat potential with a tiny, tiny stroke. You have to appreciate just how fine-tuned that is. So it doesn't actually address the fine-tuning problem at all, and it brings in another one. It's doubly ugly. Nevertheless, if you look at the literature, there are a few thousand papers written on quintessence. And the same applies to attempts to modify gravity on large scales. You can say gravity maybe propagates in more dimensions and gets diluted on some particular scale. But the natural scale of gravity, there's only one, that's the Planck scale. That's 10 to the minus 38 meters or something. But you all want to make it 10 to the plus 28. So therefore you do exactly the same tuning. You put in the Hubble parameter by hand, or its inverse in this case, so as to mimic vacuum energy. Some people say maybe gravity you can have massive gravity, the graviton can have a mass. But then you have to give it a mass of what is the Hubble parameter. In every case when you try to explain away dark energy by something else, you have to put in by hand the Hubble parameter, which as I've emphasized before is not a fundamental quantity of any kind. So all these models, I shall be restrained, are somewhat contrived, I think. If you had a good taste chip in your brain, you would not consider them worth studying. And yet, they are being studied because we are in this curious state in cosmology where you have apparently got a model that satisfies all the data, but whose fundamental theoretical basis is unsatisfactory, to say the least. You can't even make lambda of order the Hubble parameter always rather than Hubble parameter today, because in that case you can see trivially I can take it on the left hand side, and that just means I renormalize Gn by about 30%, but that's actually already ruled out experimentally, and also it will not give you accelerated expansion. So I say that there is no physical explanation for this, and that is what leads me to question the analysis, because I wonder if lambda is seen to be of order h0 squared, because that is just the sensitivity we have in the current theoretical framework used to analyze the data. And that h0 enters into every cosmological measurement. So it is easy for it to feed into the value of the only unknown parameter that you're trying to fit. And I'll illustrate this with 2 examples. How am I doing for time, Polish? Sorry, I've taken rather too long about the introduction, but rather than just show you lots of curves, I wanted to emphasize to you how important this issue is. Now, the first question you might ask as experimentalists, is you showed us this FLRW metric, which is exactly isotropic and homogeneous. What does the real universe look like? Einstein didn't know this, Lemaitre didn't know this, Robertson-Walker didn't know this. We know it today because we have actually mapped out the universe out to about 600 megaparsecs. This is from the Sloan Digital Sky Survey. And the nearby 200 megaparsecs has been mapped out in great detail by Brett Tully and collaborators. We are in the center of this picture, and these thin lines that you can see are local velocities. If it was the Friedman-Robertson-Walker metric, these lines would be all radial. Everything should be going away from everything else. But it doesn't, because there are peculiar velocities. The universe is not homogeneous. There are these huge clumps of matter, Coma cluster, Hercules cluster, we are in the Virgo cluster, we are moving towards Shapley, which is a supercluster. We are all part of Lanakia, which is the supercluster that Brett Tully and collaborators have named our home. And it certainly does not look homogeneous and isotropic. And indeed, We can therefore ask whether approximating as exactly homogeneous is actually valid, whether it is valid to assume that we are a typical observer, coming back to the cosmological principle. It should surely matter if I'm located inside a high-density region or a low-density region. It should really matter whether I'm looking along a direction that is free of stuff or in which my view, my line of sight will go through a lot of matter. These questions have never been asked in cosmology. I find that amazing that we have accepted this model without coming back to basics. The first point is that the universe is not isotropic about us. So Dennis Sharma, who I was fortunate enough to work with at Oxford when I first went there, predicted in 1968 in a paper that, by the way, has already had 12 citations to date, that we must see an anisotropy in the microwave background because we are not in the reference frame in which the expansion is isotropic, because we have a peculiar velocity due to the attraction of local lumps of matter. And soon afterwards, this anisotropy was seen on the sky. This is what the microwave sky actually looks like. You see a change in the temperature by about 1 part in 1,000 from one direction to the other. And that is simply a relativistic effect. When you move through a plant bath, you will see a higher temperature in one direction than the other. And according to the angle cos theta, beta is the velocity. Since our velocity is of order, well, since the temperature changes of order 10 to the minus 3, our velocity must also be 10 to the minus 3, around 300 kilometers per second. In fact, it has been measured precisely by Planck to be 369.8 kilometers per second, and we know the direction. But that's not all. We are moving around the sun, of course, but the sun and Earth are moving around the galaxy actually in the opposite direction to the direction towards this hotspot. So the two velocities basically add up. And then you find that we are, of course, bound to Andromeda, our nearest galaxy, which is, we are falling towards each other, will merge in another 5 billion years. And this local group is moving coherently at about 620 kilometers per second. So in this cartoon, which I have taken actually from John Smoot's Nobel lecture, you can see that we are supposedly moving towards the something which he has called the great attractor. This was believed to be the large mass concentration that is pulling us, giving us this huge velocity. And the idea is that although there are these inhomogeneities on local scales, if I average over bigger and bigger scales, then essentially I can describe the universe as more or less homogeneous on large scales. That's the idea, right? Is that really true? Now, what we do is we transform all the data that we take at Earth from all our telescopes and satellites. We do a special relativistic transformation to this CMP frame in which this thing should look isotropic, believing that to be the frame in which the Friedmann-Levent equation should also hold. Does that reference frame actually exist? This is the question we have set out to pursue. First, let me tell you about how we actually do cosmology. So one favorite tool is type 1 supernovae, which are believed to be thermonuclear explosions, perhaps as a result of the merging of two stars in a binary system, or one star that is accreting mass from a supergiant. We don't really know how it really happens. All we can do is to observe them, and we observe them using modern techniques, CCD cameras in many different color bands. These are some of the jargon you have to learn. And the magnitude astronomers use is the log of the flux, which they then multiply by minus 2.5 for some historical reason. And they quote this number. And you, of course, also know the magnitude in different bands. And the great advance in cosmology has been made possible by CCD cameras, which can image the sky night after night. So if you see a new star in the sky, that's a supernova, you can go back 2 weeks before it appeared and look at what was there in the CCD camera then. So that's how you get the rise of the light curve. And this is crucial to supernova cosmology because they are not standard candidates. There is a huge scatter. Remember, this magnitude is a log parameter. So there is a huge scatter, but in fact, it was realized that you can reduce the scatter by using an empirical correlation that is found between the magnitude and the width of the light curve. It's called the Phillips relation. And using that empirical correction, we can use supernovae as so-called standardizable candidates. magnitude that is related to the cosmological parameters in the standard model through this equation here, through this luminosity distance, and all you have to do is to measure this mu as a function of z, and then work out from the fit what these cosmological parameters are. And in fact, that is how the evidence for lambda was obtained by the two collaborations which were awarded the Nobel Prize for this in 2011. But of course, to determine h naught, you know the absolute magnitude you need to know. For that means you need to actually have a distance ladder constructed from nearby to the distant universe. Actually, you don't even need to use a model. You can just do a Taylor expansion in terms of the kinematic variables. The h naught is the first change of rate of change. Q naught will be the rate of change. The jerk is the rate of change, etc. This works fine up to the catalogs that we have today, which basically go up to redshift of 1. Right. Now, when we do cosmological analysis type 1 supernovae, you have to remember that they are not uniformly on the sky. So this is the redshift distribution of the supernovae. About half of them are very close to us. Those are the red points which are indeed more or less roughly uniform on the sky. However, the most distant supernovae at redshift beyond 1, there are only about a dozen of them seen with the Hubble Space Telescope, and they are just a few points here and there. And most of the big surveys, the Supernova Legacy survey here and the Sloan Digital Sky survey, they are, this SNLS is only at these 4 directions. They're pencil beams. Sloan is just this little strip here. We have not mapped the sky. And most of the time, we make up for that ignorance by simply assuming that whatever direction you look at the sky is typical, and therefore you don't need to know what is on the other side. It might turn out that it's very different on the other side. I'll show you an example. So what you then do is to measure the magnitude, you measure the redshift, and these x and c are the factors used to stretch the light curve to make it all fit, as I showed you. Note that all the redshifts have already been transformed to the frame, the putative frame, the hypothetical frame in which the CNT is supposed to be isotropic. Okay, I'm going to go very quickly now because I'm running out of time rapidly. We have taken that data and asked whether the magnitude actually corresponds to the distance as measured by the luminosity. If they are brighter than we expect them to be, then it's a red spot. If it is fainter than we expect it to be, then it's a green spot. If you add this sparse data together, there's only a few hundred supernovae, you find that actually there is an asymmetry in the velocity, which is this big patch here. Okay, this black dot is the supernova, the CMB dipole. You also get a more true dipole from this data in the same direction, from which we can do tomography. You can take slices of redshift and ask what is the velocity. Now, according to the standard model of cosmology, that velocity should be dying out as I go to larger and larger scales. We don't find that. Now, admittedly, the error bars are huge. We cannot exclude that at more than 1.5 sigma. It's not significant. But many groups are finding the same thing. In fact, this is one which actually did the same tomography exercise that we did. You can see the kind of dipole that we see in the supernova distribution, which becomes fainter as they go to a large redshift. This is the limit of their data, 0.06, which is about the Shapley supercluster. It's at 260 megaparsecs. And they find that, in fact, in order to explain this velocity, you have to, if you invoke a mass that is pulling us, you might ask, how large does that mass have to be? Well, that mass is increasing as you go further and further out because of the 1 by r squared law. It's already up to 10 to the 17 solar masses up to the point you've exploded. But if you look at the telescope, you don't find anything there. There is something mysterious going on that we don't understand. And I'm prepared to bet that you have not heard of this problem before. These are not talked about in polite society because it doesn't quite gel with this usual assumption that if you average over large scales, we should converge to the CAP frame. All these velocities should die away. Here is some recent data from the 6 degree field galaxy redshift survey taken from Australia. This is the 95% confidence level band from the Lambda CDM, and the measurement is very clear on that. So let me then point out.
You have 5 more minutes.
Thank you. Similar asymmetries have been seen in X-ray clusters. Let me come to the punchline of my talk. If you pick up a textbook, this is a good textbook by Jim Peoples, it shows you an illustration of the sky of radio sources which have been mapped from the Green Band telescope in West Virginia. There are only about 30,000 there. And this figure is supposed to impress on you that the universe looks isotropic, the sky is isotropic. You might ask, what are these funny lines here? That actually is the Milky Way. These holes are there because from Green Band you can't see the whole sky. So there are bits of the sky you don't observe. But in fact, this statement is incomplete. If we are actually moving, then the sky in objects, distant objects, cannot be isotropic. It must also have a dipole asymmetry. And this was highlighted by George Ellis and John Baldwin, a radio astronomer from Cambridge, and Ellis is a radiologist from South Africa. They pointed out that if a moving observer should see objects of the sky displaced a little bit, this is a phenomenon called aberration. It was first discovered by James Bradley, who was in fact the civilian professor of astronomy at Oxford, and he discovered this 280 years before special relativity. It's a special relativistic effect. And in fact measured the speed of light to within 10% using this effect. Apart from that, if the sources have a power law spectrum, as they typically do for quasars and radio sources, then you also have the Doppler effect, because the source is coming towards you, the frequency is shifted towards the blue, and therefore you're sampling a different part of the spectrum than you would had you been at rest with respect to each other. You put all that together and you get a formula for what dipole you expect in terms of the velocity. Is the same term that came in the CMB dipole, but now it's enhanced by this x and alpha, which are just the exponents of the number distribution at the spectrum. Now, what we therefore need is a lot of these guys in the sky, and we need to measure the dipole and compare with that, because that will tell us whether this kinematic interpretation of the CMB dipole is actually correct. Of course, you have to worry about the possibility that some of these quasars or radio sources might accidentally be very close to us, in which case you get a huge dipole just from that fluctuation. And you also, of course, need a lot of them to beat down short noise that will go as root n. So these are the things you have to watch out for. The first time we are able to do this test was when this NVSS catalog of radio sources was released from the Very Large Array in New Mexico. It was in 2000. Only in this millennium have we been able to do this test. They had about 600,000 radio sources. Then a satellite called WISE, which surveyed the sky for many years, that released a huge catalog. They actually had 7 million objects. And we could use about 1.2 million of them as distant galaxies, but they were not very far away. They were at a redshift of 0.14. Here the redshift was 1, but this is estimated, not directly measured. The real breakthrough has been in the past year, when we have been able to construct a catalog of 1.4 million quasars, whose redshifts, the median redshift is 1.2. And we know that these redshifts are 1.2 because we have measured them spectroscopically using the slow digital sky survey. So let me fast forward through this just to indicate that the radio sources, you do see a dipole, you do see the expected cos theta pattern, and it is surprisingly large velocity. This is much bigger than the velocity that you infer from the CMB. The rest frame in which these guys look isotropic is not the same as the CMB. But if I do Monte Carlo simulation,